Good afternoon. Today I will continue the Laplace transform. Especially, I would like to show you how to use a Laplace transform in electric circuits. Okay. I'm using a book from Modern Mathematics, and there is an example how to use the Laplace transform in the circuit. You can see from this figure. Okay. We have a source of voltage ET here, and then we have a switch. Switch is turned on when the T is equal to 0, and then we have a three passive component R, L, and C here. So the question is determine the charge Q on the capacitor and resulting current in the circuit at the time t, when the R is 160 ohm, L is 1 Henry, C capacitor is 10 power of minus 4 farad, and AT is 20 volt. So this is the DC. Okay. So we have to apply a Kirchhoff's second law in the circuit. So we got that this is the loop here. So Kirchhoff's second law say that voltage in the closed loop must be 0. So if we make a summation of this voltage, and there, so it must be 0. Or AT equal to VR plus VL plus VC, like this one. Okay, so we can translate this using this one. So this is the ET, and then this is the VR, and this is the VL, LdI per dt, and this is the VC. VC is 1 per C integral of E dt is equal to ET. Okay, and then we can use because this is the integral, so we can use the integral, or we can use the differential here. So because of the I, the current is a differential of the charge dq per dt, so we can write this equation become these equations. L d quadrat q per dt quadrat plus R dq per dt plus 1 per ck. So this is the key is equal to ET. And then we substitute the value of L, R, C, and AT. L is 1 Henry, R is 160, and C is 10.4 farad. So we have these equations. Okay, so from this equation we take a Laplace transform for the differential. Okay, so differential the s quadrat plus this is 160s plus 10 power of minus 4 ks. So this one is key, so we translate to ks here, and then this one is this is the initial value of the key is 0. So we only convert from DC 20 to the Laplace is 20 per S. So we can reduce this equation. So actually this is belongs to this one. This one is belongs to the Laplace of differential order 2, and this one is belongs to differential order 1. So if you check the differential, okay, here maybe in this one we can find what is the, if we have the differential equations, okay, in this book. So this is the integral and this is the differential. Okay, derivative. Okay, and then derivative is this one. Okay, so this is the second order derivative, so we can get this one. S squared fs minus sf0 plus minus f accent 0. So because this is the also the second order here, okay, here, so this is belong to here, or I can see maybe like this one. The simplest one is s squared minus s key 0 minus key accent 0. This is the differential of this one. Okay, so this is the Laplace transform of this one, and for the second part, first order this one, the differential is 160 s minus 160 key 0. Okay, so we can write this one because of all its initial value is equal to 0, so we can reduce this equation, become these equations. Okay, so we got that key s here is equal to 20 per s multiplied by s squared plus 160s plus 10 power of 4. So we can solve. After that, we have to solve using the partial fractions, and then we got this one, and then we can inverse. We got this one. Okay, this is later. I will tell you maybe in next week how to inverse from the S domain to time domain. But here, maybe the final is this one. The final answer for today is this one. So how to determine the key S here from the circuit? So after this one, we have to make the inverse Laplace to get the appropriate answer. Okay, so this is the first, and the second, if we have the parallel like this one, for example, we have the DC voltage 200 volt. We have R1 20 ohm, L1 is 0.5 Henry, and then R2 is 8 ohm, L2 is 1 Henry, and R3 is 10 ohm. So how to solve using the Laplace? We have to apply Kirchhoff law in node X. This one here. We apply Kirchhoff law. I here, this is the I, equal to I1 plus I2 here. I1 and I2. Okay, so applying Kirchhoff's second law to H the loop. Also, we using the loop we can see, because the I is equal to I1 and I1 plus I2. So here, this actually in this loop. Okay, in this first loop is ET is equal to IR1 plus L d1 per dt, like this one. Okay, so we use this equation to replace I here. So we got these equations. Okay, ET is 200. Okay, and the second loop is here. L2 d1 I2 per dt plus R3 I2 minus R2 I1 is equal to 0. So we substitute for the given value of the resistance inductance from the first equation and second equation. Okay, so we got this one, and then we take a Laplace transform of this one, of two equations above, and then the initial condition is equal to 0. So we can write like this one: dE1 plus dt plus 66 I1 plus dI2 per dt plus 40 I2 is equal to 400. Okay. Okay, so this one, the Laplace transform was given, this is S. So this one. So S plus 56 is this one, and then s plus 40, this we transfer to Laplace, we got this one, s plus 40 into s, and then 400 we transfer to Laplace like 400 per s. And then the second equation is minus 8, this one, I1s plus, for I2 is s, this is the s plus 10, I2s is equal to 0. So this is the second question. This is the Laplace transform of first question, and this is Laplace transform of second questions. Okay, so we got that I2s from first equation and first equation and second equation is become this one. I2s is 3200 per s multiplied by s quadrat plus 74s plus 180. So we can divide the second part using this one. So after that we have to inverse back to the time domain. So this is the final for this week. So I show you how to use the Laplace transform to solve the time domain, and after that we can get, if we get I2s, we can get I21, I2t, and I1t. So yeah, I think this is a simple. Then if we use the ordinary differential equation to solve these circuits. Okay, so I think these two example is enough for today. Maybe I will talk later how to get the final answer, how to inverse from the S domain in electric circuit to time domain to get the final answer. Okay, thank you for today. Good afternoon. Assalamualaikum warahmatullahi wabarakatuh.